So first of all, I should thank the organizing committee for giving me this opportunity to present in this workshop. And today I'm going to talk about recent developments in the higher twist formalism. And in this talk, I will mainly focus on two studies that we did in past couple of years.
哎呦，你去赚钱了，我开会了。
你开会了是吗？
Sorry. Okay. This is the outline of my talk. First, I will give a brief introduction on parton energy loss in deep inelastic scattering. Then I will go through some prior work on jet quenching. Here, I will mainly focus on next to leading twist parton energy loss calculation, which uses single scattering per emission approximation. There was a dispute over collinear expansion with that calculation. And in our full next to leading twist calculation, we were able to address this dispute. In the second part of my talk, I will talk about multi-stage evolution and the importance of high virtuality phase of the energy loss. Parton energy loss in deep inelastic scattering has been studied for many years. And one of the most important study was done by Guo and Wang back in early 2000. Here they calculated drag and radiative energy loss of an energetic parton using high twist formalism. In their calculation, they use single scattering per emission approximation, which is valid for high virtuality partons. When partons have lower virtuality, they tend to have multiple scattering, and there are several studies that use multiple scattering to study parton energy loss, transverse broadening, and etc. A diagrammatic representation of deep inelastic scattering can be given by this diagram, and the differential cross-section for DIS is given by this equation. Here, L mu nu is leptonic tensor and W mu nu is hadronic tensor. Since parton energy loss is associated with hadronic tensor, I will mostly talk about hadronic tensor in this talk. At leading twist, there's no medium interaction after hard scattering. Therefore, we can consider this process as vacuum-like. This is the leading order contribution to the leading twist, and this is the next to leading order contribution to the leading twist. There are additional higher order contributions, and one can resum these contributions order by order to calculate renormalized quark fragmentation function, which satisfies the Dirichlet evolution equation given here. When it goes to next to leading twist, one need to use single scattering per emission approximation as they did in GW calculation. And in their calculation, they use soft and collinear emission as well as rare gluon exchange approximations. They only consider the final state modifications as they study the modifications to the fragmentation function. And there are more than 20 Feynman diagrams contributing to next to leading twist, but 19 of them are gluon exchange diagram. The diagrams with the quark exchange are suppressed by the virtuality, therefore they can ignore in the limit of next to leading twist. These medium interactions modify the evolution of fragmentation function. And if we need to calculate higher twist, we need to consider multiple scattering per emission. In this study back in 2012, considered the possibility of multiple scattering by using arbitrary number of scatterings. Therefore, we can reduce to any number of scattering by using this result. And this is a realistic approach for partons with any virtuality, but the final result has not been implemented in the numerical simulation. In this talk, I will mainly focus on next to leading twist. And first, let's talk about GW calculation. And in their calculation, they use all 19 gluon exchange diagrams, and they use collinear expansion around k-pep equal to 0 to calculate next to leading twist contribution to the hard part. Here K-perp is the transverse momentum of the exchange gluon. And importantly, they ignore the K-perp dependence in the phase factors in their calculation, which lead to only one contributing diagram as shown here. Because of that, their result is simple. The medium modified kernel can be given by this equation. And numerical implementation of this equation is convenient, and the medium modified fragmentation function is the product of medium modified kernel and the vacuum fragmentation function, which satisfies the medium modified Dirichlet evolution equation. Along with the vacuum kernel, there's medium modified kernel so that we can describe the deep inelastic scattering. To graphically represent the medium modified kernel, we use the last part of the medium modified kernel, as the first part given in red color is common for all three studies that I'm going to talk about in this talk. And when we plot the medium modified kernel for GW calculation, as you can see here, the result is positive definite, and there will be mild fluctuation at higher path length. Now let's talk about the dispute over collinear expansion. As I said earlier, in the GW calculation, they ignore the K-perp dependence in the phase factors before twist expansion. The argument is that at very high energies and shorter medium lengths compared to formation time, one can ignore this K-perp dependence. But later, Orange, Sakrao, and Sarkert argued that K-perp dependence in the phase factors can be significant in the media longer than formation time. Therefore, they calculated the only contributing Feynman diagram in GW calculation in the limit of soft and collinear gluon emission. Their result is given in this form, and as you can see, there are two additional contributions compared to GW result. Because of these two additional contributions, this result is oscillatory at high path lengths, and it can go to negative, as you can see in this plot. This comes to our full next to leading twist calculation. The main reason for doing this full next to leading twist calculation is that both GW and SEC calculations are somewhat incomplete. Because in the GW calculation, they ignore the K-perp dependence in the phase factors. On the other hand, in SEC calculation, they only considered one Feynman diagram. Therefore, one can argue that the other 18 contributing diagrams can have significant contribution when K-perp dependence in the phase factors are considered. Therefore, in our full next to leading twist calculation, we consider all 19 Feynman diagrams with gluon exchange. We ignore the contribution from quark exchange diagrams as they are suppressed by virtuality in the limit of next to leading twist calculation. And here we didn't use soft and collinear gluon approximation, and K-perp dependence in the phase factors are considered for all the diagrams. After doing this calculation, we found out that a total of 7 contributing diagrams in this calculation without soft and collinear gluon emission approximation. And if you use the soft and collinear gluon emission approximation, these contributing diagrams drops into 5 contributing diagrams. Therefore, we can say that even with or without a soft collinear emission approximation, there are additional contributions coming from the set of 19 Feynman diagrams. These additional contributions are given in this figure, and the two diagrams outlined with green color are non-central cut diagrams. Those non-central cut diagrams have phase-space constraint coming from the vector potential correlator. Because of that, there's an additional factor ranging from 0 to half will come into this result. The two Feynman diagrams in red outline are cross-scattering diagrams, and the two Feynman diagrams in outlined in blue color are pre-emission scattering diagrams. Here, pre-emission scattering means the scattering happens before the emission. These diagrams are usually suppressed by momentum fraction in the limit of soft-gluon approximation. But when we use K-pub dependence in the phase factors, not all terms are suppressed by the momentum fraction. The medium modified kernel from the full next to leading twist calculation is given by this equation. And as you can see, the first three terms have additional momentum fraction dependence, but the last term does not depend on the momentum fraction. Because of that, we compare this result for different momentum fractions, and there's a considerable difference between the results. And when we increase the momentum fraction, the contribution from medium modified kernel decreases. Because of this additional momentum fraction dependence, numerical simulation can be complex, as one need to include medium modified kernel into the momentum fraction integral. Here we use n equals 0 for convenience, and here n is phase space constraint that I explained in the previous slide. Here n can be ranged from 0 to half, depending on the strength of the correlation. Because of that, we show our result as a band. Here, lower line of this band is correspond to n equals half, and upper line of the band correspond to n equals 0. If we and this result is positive, definite, and increasing with path length. And if we ignore the contribution from pre-emission scattering, there's no momentum fraction dependence, and this result reduced into this purple dotted line as shown here. Now let's compare this full next to leading twist result with GW calculation at high virtuality. Above formation time, one need to include, one need to multiply the medium modified kernel by wave packet. And here we use Gaussian envelope function from vacuum emission. And as you can see here, there's a slight shift in SEM result, but the total area under the curves looks similar. Therefore, we use the integral of this medium modified kernel multiplied by the Gaussian envelope function with respect to length to see how it changes, how the area changes with the length. And as you can see, after about 3 formation time, this saturates, and the saturation value looks similar for GW and SEM case. Therefore, we can assume that the difference in high virtuality case cannot be significant in this case. When it comes to low virtuality portion, to compare SEM and GW kernels, we use accumulative energy of emitted gluons, and here also we use n equals 0 for convenience. And to get this plot, we use 100 GeV quark with a fixed Q hat of 1 GeV squared over Fermi. And as you can see in this plot, at small path length, SEM result is comparable with GW result, but when it goes to large path lengths, there's a significant difference that can be observed. Therefore, to get better understanding, one need to do a full Monte Carlo simulation of jet quenching through a realistic hydrodynamic medium using multi-stage evolution. And from these results, we can say that this SEM modification can be important in low virtuality phase, as they have large formation time, therefore they can take radiation longer than 1 Fermi. But when it comes to high virtuality phase, they may not have significant effect. Now let's move on to the second part of my talk. Here I'm going to talk about multi-stage evolution and the importance of high virtuality part. There are at least two stages of the partonic shower, high virtuality stage and low virtuality stage. At high virtuality stage, virtuality is usually larger than the scale of the medium. Therefore, one can use declap evolution. But at low virtuality stage, virtuality is in the order of scale of the medium. Therefore, one need to use multiple scattering per emission approach. Usually, the importance of high virtuality stage is underrated. The main reason for that is at high virtuality, formation time is small. Therefore, number of scatterings is also small. Therefore, the parton shower is usually assumed to be vacuum-like. In this study, we study the importance of high virtuality part within a multi-stage event generator. Here we use Jetscape 0 as a multi-stage event generator. Jetscape is a general modular and extensive framework that can be used to simulate high energy collisions. And here we can use multi-stage evolution using different stages depending on the virtuality and energy. Before going into the comparison, let's talk about vacuum versus medium modified splitting functions. When we increase the virtuality scale, as shown in these graphs, from left to right, we increase the virtuality. The medium contributions, the relative medium contributions decrease. Because of that, we can say that medium modified part is a perturbation to the vacuum term. But at low virtuality, medium contribution can be comparable to the vacuum. Therefore, high virtuality formalism is invalid. Therefore, one need to use low virtuality transport description. To compare the effect from the high virtuality phase, we use vacuum splitting function and medium splitting function in the high virtuality phase in the multi-stage event generator to compare the number of scattering and average time spent in high energy and low energy stages. Here, the two plots in the top are with vacuum splitting function, and the bottom two plots are with medium splitting functions. And the two plots in the right are showing the average time spent in each stage with respect to energy of the parton. And the left-hand side plots shows average number of scattering in different stages with respect to energy. As you can see in these two top plots, even with vacuum splitting function, we can see significant number of scatterings as well as parton spend significant amount of time in the deglap stage at high energy. But when we include the medium modified splitting function, the number of scatterings as well as average time spent increases dramatically. And as you can see here, below around 60 GeV, transport stage dominates over deglap stage, but after 60 GeV, deglap stage dominates over transport stage. Because of that, we can say that Rick energies can be different from LHC jets. To experimentally compare, the effect from multi-stage evolution, we can use experimental comparison using deglap evolution and multi-stage evolution. Here, for the vacuum shower, we use matter vacuum shower down to 1 GeV, and for lead-lead collision, we use matter plus LBT for the deglap plus transport and matter for the deglap stage. As you can see in this graph, deglap alone shows excellent agreement at high PT. But when it comes to low PT, suppression is not sufficient to describe the experimental result. But when we include deglap with transport using multi-stage event generator, we can describe all the entire PT range. This emphasizes the importance of multi-stage evolution. By saying that, I'm going to conclude my talk. Here, we did full next to leading twist calculation to address long dispute over collinear expansion. here our results are similar to GW at high virtuality, but at low virtuality, there's a considerable difference if we go to higher path lengths. This can be considered as a one step toward more precision calculation, and this can be also important for theoretical predictions for high luminosity LSC and SPNX runs. Also, the high virtuality phase of the parton shower has significant impact on the high PT partons. And lastly, multi-stage evolution is required for an accurate description of the experimental results. Thank you.
Thank you. I think we were muted. Sorry about that. Thank you for the nice talk. We have time for questions now. We have at least one in the room.
Hi, thank you for the talk. So in the first half of your talk, you talked about the medium induced emissions, and during the morning, there were several talks about like how can you calculate this and different limits. And I was just curious that if you have a plot or have you compared to, you know, these other things, like how your result is related to the opacity expansion or how your result is related to the harmonic oscillator approximation. Where is it valid? Where is it not valid? Can you tell something about that?
So we still don't have like comparison with other approaches like BDMPS or anything, but what we can say is usually this formalism is valid in high virtuality partons. In the low virtuality partons, LBT uses this to gluon as a gluon emission distribution. So this is like this is mostly valid in high virtuality portion. That I can say.
Okay, further questions, Shinyan.
So, oh, I was looking at the speaker somewhere here, but sorry. So, if I understand, you are not really calculating extra diagram. I mean, you still only have those diagram with like two glue exchange with your target and with another radiation coming out, right? I mean, if you look at the original, yeah, I mean, for example, this is, you still have just two gluons coming down, right?
Yeah.
You are not looking at like extra diagram with like full gluon exchange with the target. You only have
we are only looking at the similar
those diagrams originally is there in our original calculation. It's just they don't contribute at the leading twist. And now, if I understand right, you're looking at these diagrams, but beyond the leading twist. Is that correct?
No, actually, we are looking at the next to leading twist, but we included the contributions coming from the phase K-pop dependent terms from the phase.
Yeah. That's all. Yeah, I know. That's what I'm saying. I mean, this is, you're just looking at the diagram essentially like the same, but you're looking at the those diagrams. If you don't consider transverse momentum stuff like that, they will not contribute to the leading twist. I mean, the result we have before. You are just now include the some momentum transfer, so they do contribute at the next leading twist. I'm just trying to understand this. So in that case, if you go to your equation, your page 12, here. So apparently that's the correction come from. You have power law C over tau F square, right? That's the actual.
Yeah.
Yeah. And
Yeah.
that is, has some kind of power coming from, that is understandable. But if you in the same spirit, you should also probably expand the first term. And the first term, if you expand it to, C over tau square, isn't zero in principle. Right? It's just the cancel. So if you're only looking at the power of C square, the last term is the only term you have.
Yeah.
If you really do the consistent the power counting.
Yeah. I agree with that. Yeah.
Yeah.
Okay, let's go to Zoom. Abhijit.
Hi, can you guys hear me?
Yes.
Yeah, I just want to slight disagreement with Xinyan here. So it's still the same. It's still next to leading twist. Okay, it's just that you have to include these factors that come from the phase. I think in the original work, the argument was that you did not have to consider the corrections, the next to leading twist corrections that came from the phase, because the length of the medium could be very short compared to formation time, right? And if you take that away, which is I think what Orange and Zakharov and all these people were arguing, is that, okay, if you have a longer medium, then you have to put these in. But all we are arguing is that if you do put them in, then many terms start contributing, not just that one term that you had in your in your first paper. That's it. And the end result is not very different from where the original from your original work. I just wanted to comment to the other question as well that came up, is that in the higher twist formalism, one calculates the correction to splitting from a matrix element. And usually one does not specify the origin of that matrix element or how to calculate that matrix element. One just leaves it as this FF correlator. If you then want to go and put in an approximation for the harmonic oscillator, for anything, for HTL, anything you like, you can put that in there. Okay, but it's this is a more general approach where then you can then approximate the kind of medium you want.
Okay, thanks, Abhijit. Let's move on now. So let's thank Chaturanga once more